All right, hello. This video is going to be about the twin primes and the twin prime conjecture. And over the last decade or 12 or so years or 15 years, I wrote 2 different papers about the twin primes. I had one method, and that was the way that my mind initially saw and tackled the problem. But then there was part of that method that I didn't fully explain, and it kind of led me to a second method, which I then was much better. And the second method is much more formal. And so I wrote these 2 papers, and eventually I consolidated them into one paper just to have like all my material on the topic in one place. So I'm going to go through and talk about these. Now, I'm doing this on the fly. You'll have to bear with me. I haven't read these in a year or 2, and I haven't really worked with them in a long time. And maybe I should have refamiliarized myself with it first, but I think this will just be good for me to jump in. I remember all the basics, of course, but you'll have to bear with me if my mind slips on some of the exact specifics. We'll see how it goes. I also think this will be quite a lengthy topic. This video will probably take a few hours. I most likely won't do it in one sitting. I'll do it in 2 or 3 or 4 or wherever it naturally seems like good places to stop. Maybe I'll do the 2 papers in parts or whatever. But I'm just going to start going again to get people familiar with this, and for people who are real math heads or like this kind of topic. Maybe over time I can make some other content or better visuals or something else. But this is what I have to work with right now. So we're going to go from there. So just bear with me a bit as I kind of stumble through my own work and try to refamiliarize myself with stuff and just talk about it. You can always get the paper or ask questions, and I can always make supplemental material. So this is going to be a real math-heavy video, just discussing some topics. And let's see what we get. So, the twin primes. Okay, and let's see. Where do I want to jump in on this? So you can see some contents here. And this abstract that says kind of what's going on. I'm not going to really go over that, but I just want to kind of get to the beginning of the paper. So let's see. So here's the table of contents. And this introduction is kind of what I was just saying. Over the last decade, I explored finding a proof of the twin primes. I developed 2 related but different approaches. And so here's a basic, outline. One of the approaches is based on dragging lines across hyperbolas and parabolas and how that relates to certain surfaces. And I found the approach adequate, though its final steps, it relies on a statement that the range of 2 surfaces is not a basis for all, but a finite amount of odd numbers. And when we get to that part, which will be the end of the second paper, while for some it may seem readily apparent from the surfaces that the statement's true, a complete proof requires something a little bit more rigorous. And so I sought to explicitly prove that same statement, and which led to the second proof, which is actually the one that we're going to cover first, and the better, more formal proof. And then I just give some background. These were some of my earliest writings. I hadn't even learned LaTeX yet a bit, or programs that could convert things into LaTeX and whatnot. And so some of the earliest versions of my first proof on this were just, they were legitimate, but they weren't really up to what you would look for, like a format or a standard of what people expect when they come to see a proof. So a lot of this was me rewriting stuff because I wanted to make it look better and explain it better and so forth and so on. So proof number 1, this first proof of the twin primes, I feel that I can prove that there are infinitely many twin primes. And I might come back to it during the paper, but once you see this technique that I use to try to prove the twin prime conjecture, it actually, there's maybe, and I'm not going to remember them all off the cuff right now, but there's like 5 or 6 or 8 other problems that are all almost exact duplicates of this, or very closely related to the same idea and the same technique. And over time, I feel like some of these problems I could probably solve or write up a paper or a proof using the same method, but I haven't gotten to that, or I haven't quite figured out little parts of each one. Some of them I've tried, and I realize that they're harder or easier than others. And what am I talking about here? So I'm talking a thing with like there's a lot of questions like, are there infinitely many Fibonacci primes? Are there infinitely many Mersenne primes? Are there infinitely many Sophie Germain primes? I think it's the perfect odd number question is another one. Goldbach's conjecture. And I know I'm not remembering them all right now, but there's like 4 or 5 others, and there's a whole host of them that they're all almost identical within the framework that we're going to use. But this is the one that I happen to think of and see first, and how my mind works of it first. So I just wanted to mention that now, because it might come up while I'm discussing it. My mind tends to go back to some of these things. But we're going to try to prove the twin primes here, that there's an infinite number of twin primes, and how would we go about that? So I call this one, proof 1, infinite twin primes from the rows of twin surfaces. And some of this will be me just reading what you see on the screen, but then once I get a sense of what I wrote, I might just start paraphrasing or talking about whatever I think needs to be expanded or amplified more or talked about specifically. Okay, so, we say here a basic introduction. The twin prime conjecture is a well-known topic within the field of math regarding whether there are infinite twins, primes separated by a difference of 2. And this proof that we're going to talk about first generally uses a strategy that I split into 2 halves. So this is a very big, rough outline of what we're going to do here, and how you'd go about proving the twin primes have infinite twin primes. First, there are 2 surfaces are determined such that choosing any natural number which is not found on either surface generates a twin pair. So we come up with 2 surfaces so that if you choose a number that's not on either of those surfaces, a natural number, you can then use that number through other formulas to generate a twin pair. And then the second part is to then show that there are an infinite such of those natural numbers that are not on either of those surfaces. So that's going to be the general strategy that we take. We come up with 2 surfaces, and I'm just reiterating and repeating myself now, but we come up with 2 surfaces, and you find a number that's not on either, a natural number. So we're only dealing in integers or whole numbers here, specifically the naturals. So you take these 2 surfaces, you find any number that's not on them, and we can show that a number that's not on them can be used to generate a twin pair, and then that there's an infinite number of those numbers that are not on the surfaces, i.e., or therefore there are infinite twin pairs. And specifically that anytime you get a number that's not on the surface, it always generates, a twin pair without, and a different twin pair, different numbers not on the surface generate different twin pairs without exception. So that's just going to be the general strategy that we try to follow. So the first part we're going to talk about is this infinite twins from the 2 surfaces. So this is some of the facts, and I'm not sure yet if I just want to read this or if I want to just tell you, because I know this part by heart pretty well. You would think or hope I would at this point. So I'll read this a little bit. So these are the facts and the givens that we're going to use to start off with to create our initial surfaces and our initial formulas. So you're going to use the fact that all primes except the number 2 are odd. So 2 is the only even prime and all other primes are odd. Great. This means that all other primes other than the number 2 can be expressed in the form of 2n plus 1 for some natural number n. Doesn't mean all 2n plus 1 are primes, just that primes are odd numbers. That's all I'm saying here. So all primes except the number 2 are going to be an odd number. That's all we've said here. So next, use the fact that all numbers except 1 are either prime or an odd composite. So if you have an odd number, it's either a prime or a composite. That's all we're saying next. That fact is going to be important here in a second. So we know that all primes are odd except 2, and that if you have a prime, it's either an odd composite or it's prime. Kind of redundant, but this is just stating the obvious. But that means that all odd numbers greater than 1, which are not composite, are prime. Seems pretty obvious by default, but it's just this is where the proof gets off the ground. So we're using the fact that all odd numbers greater than 1, which are not composite, by default must be prime. Okay? Thirdly, we're going to use the fact that all odd composites, so all the odds that are composites, they're the product of 2 odd numbers greater than 1. So because of the rule that an odd number times an odd number gives you an odd number, that all odd composites are the product of 2 other odd numbers. They're not prime, so they're not just 1 in the prime. So odd composites must be the product of two odd numbers greater than 1 if they're not prime. Okay, great. So this is the first formula that we're going to use. Is we're going to put all those facts that I just said into a formula. And these three givens are expressed as equation 1, which is interpreted as stating that the primes are all odds greater than 1 that are not odd composites for natural inputs N, A, and B. So that's what you see here. And I think, I don't know how, I might zoom in just a little bit more. There we go. Make it nice and readable. So the primes, which we're saying are equal to some 2n plus 1, not all of them, we know that, but we're just going to start with that. Whatever this 2n plus 1 is, it's an odd number, we know that. And you'll see I've used the does not equal sign here. That's very on purpose. So a prime is an odd number greater than 1, so we can start at 2n plus 1. But it's not equal to an odd composite. And an odd composite is the product of two odd numbers. So here we see another odd number, 2a plus 1. So that's going to be 3, 5, 7, 9, so forth and so on. Times the second one. 2b plus 1. Excuse me. So this side represents an odd composite because it's an odd number times an odd number. And we're saying that we need another odd number that can't equal that. So we're looking for odd numbers that do not equal odd numbers times odd numbers, if that makes sense. We want odd numbers that are not the product of two other odd numbers. Therefore, we have primes. Okay, great. So that's what we're stating in this first formula here. So if a twin primes have a difference of 2, which is the definition of what we want for twins, if this odd number is a prime, we're just going to say if it is for a second, 2n plus 1 is the smaller of that pair, then adding 2 to that is the larger. So whenever this 2n plus 1 does turn out to be prime, if it's a twin pair, then 2n plus 3 must also be prime. Okay, great. So using the same logic as equation 1, 2n plus 3 must also not be an odd composite. So twin pairs are two odd numbers that are 2 away, so they're next to each other as odd numbers go, and neither of them are the product of two odd numbers themselves. So that's the logic that this whole thing starts off with. Pretty makes sense, right? So this is stated in equation 2 for the positive numbers n, because we can use the same n here, because 2n plus 1 is going to be our prime, again, when it is prime, and 2n plus 3 then will also have to be prime. But that means 2n plus 3 cannot also be a product of two odd numbers. And here, these odd numbers can be different than the first two. You know, that's fine. So they have to get their own variables, C and D. So that's why you see C and D here instead of A and B again. But the n represents those two prime numbers. That's the same n. Okay, great. So now we've said that our prime cannot be, we know it's odd, but that odd can't be an odd composite. And when that's prime, 2n plus 3, the next odd number after it, also cannot be an odd composite. Okay, that makes sense so far. Nothing to prove, nothing crazy here. We've just started with our givens and said, these are the requirements that have to hold. So simplifying these equations, you can expand this out. You know, you get 4ab plus 2a plus b plus 2. You're just doing FOIL on this. This is basic algebra. You can bring your 1 and your 3 to your other side and divide by 2, and you're left with... So simplifying this, we get that this generating number n, so whatever number would have generated our odd, the first odd, the second odd, the third odd number, so forth and so on. If that odd number can't be this product of two other odd numbers, then it means the generating number cannot equal 2 times A times B plus A plus B. And because the prime that's, you know, the odd number that's 2 more than that, which would be our pair, can't equal this, that means that generating number can also not equal 2CD plus C plus D minus 1. And that's just from multiplying these sides out, subtracting over the 1 and the 3, and dividing by 2, and you'll get these two right here. Great. So we know that we're looking for ends that are not this and not this. Okay. Now, let me read ahead for myself because I want to point out something here at this point that I want to make a point of something, and I'm not sure if I write it here or if it'd be better just to go a little further before I explain it. I think I'll go a tad further and then I'll be able to explain it because it's just going to come up in here anyway. So equations 3 and 4, these two here, represent basic surfaces in 3 coordinates, or rather anti-surfaces because we said not equal to. But you could think of this as like, you know, z equals something of x, y. I just used a and b in this case, other different variables in c and d. But this is a surface with 2 inputs and an output. So we're in 3D here. And if you notice, because this was just +1 and this was +3, and it ends up being this and this -1, these two surfaces are the same. Now, obviously, different variables control the odd factors of our composites there. But the 2AB plus A plus B is the same as the 2CD plus C plus D. If you were to graph just those, you would notice that those are the same. And the only difference is here we've subtracted 1. So that's what we're saying here is that the first thing to notice is that the second surface, the one that dictates it for our second twin, is just the same as our first surface slid down by 1. Okay, great. So all the values that we would generate by this 2AB plus A plus B are the same as these 2CD plus C plus D, except this case is going to take all those values and then subtract 1 from them. Okay, great. So I know some people don't like charts in proofs, and I'm not using the chart or to prove anything. It's a little array I'm going to show you. But sometimes just for vision in the eyes and explaining things, it's handy to have a chart to visualize things. So what you're seeing here are those two surfaces. You see AB, AB, CD, CD -1, and here they are. So we want to plot the values on AB plus A plus B and on CD plus C plus D -1. So you can see here in the, one column, 1, 1, A1 would be 2 times 1 times 1 is 2, plus 1 is 4. That's why a 4 is there. And because this is symmetric, you could swap A and B without loss of generality. But let's say one of them is 1 and the other is 2. So that's going to be 2 times 1 is 4, plus 2 plus 1 is 7. So that's why you'll see 7 here and 7 here. And if you notice, because like I said, it's symmetrical, you'll see it's diagonalized. 7, 7, 10, 10, 13, 13, 17, 17, and you go right down this diagonal for when A equals B. So this is just going to be easy to point things out numerically and easy for your eyes to see, which is why I include this. So this is 2AB plus A plus B. Great. And here's 2CD plus CD plus C plus D -1. And like we said, all we're doing is minusing 1 here. So you'll notice it's kind of redundant, but it helps the eyes. You'll notice that all the values in the second chart are all these values -1. Here's 4, here's 3. Here's 7, here's 6. Here's 10, here's 9. Here's 24, here's 23. So forth and so on. You get it. So these are the values that we're looking for. Now, I say it here, so I might as well just kind of say it, read it, and say it and explain it. Here's the key thing to start noticing how amazing this technique is and why it's going to work in the long run and what is going on here. What these two surfaces dictate is the following. Surface 1, which is equation 3, restricted to the natural domain, is an n such that 2n plus 1 will not be an odd composite. So we solve for what this n can't be when we have an odd number that's not an odd composite. That means n cannot be equal to this, which is this surface right here, right? So if we find n values that are not on this surface, and we plug them back into 2n plus 1, that gives us a prime number. And this surface really cracks open the primes in a way that a lot of people don't talk about. So I'm kind of giving you a secret here to all the primes, or what really blows the primes wide open. You can show that there's a one-to-one relationship here between the surface 2a plus 1 times 2b plus 1, or i.e., more specifically, when you rearrange it, this AB, 2ab plus a plus b, that's a direct relationship to the numbers that aren't on it to the prime numbers. Now let's do some examples before we go further, just to show you what I mean by this. And that's what I start talking about here. Therefore, choosing any natural value for n that is not on the surface, values not in the table represented by figure 1, not in this table, will make 2n plus 1 a prime number. In fact, all the numbers n that are not on that from that natural range on surface 1 generate all the primes except the number 2, without exception, and when ordered, generate them in order. So I think this is amazing right here. Give me 1 second here. I got to do something in the room. Okay, excuse me. So what do I mean by that? So this chart represents, now again, we organized it here by shuffling the 1 over, dividing by 2. But what this chart represents is all the odd composites in a way. And if you pick an n that's not on this chart and then plug it into 2n plus 1, you'll get a prime number. And it does them all and in order. So let's start up here in the corner. The first number that does not appear on this chart is the number 1. Because the first value we start with is 4. The smallest thing when a and b are 1 that this can be is 4. So the number 1 does not appear on the chart. And if I plug 1 into 2n plus 1, I get 3, the first prime, bigger than 2. So we're only dealing, because we said it was an odd, we're only looking at odd numbers that are not composite. So 3 is the first odd number that is not composite. Therefore, it must be prime. And if this is starting to dawn on you that this just cracks all the prime numbers in one way, you're not wrong to kind of feel funny here for a second and say, hold on a minute. Does this really work this way? Is it that easy? Or not that it's easy, but it kind of is in one sense. And you go, hold on, this can't be like a key to all the primes here. But watch, it gets better. So the next number that's not on this surface is 2. We haven't gotten to 4 yet. 1's not here and 2 is not here. We'll try it again. 2n plus 1 for n is 2 is 5. Hey, that's the second prime. 3 and 5. Great. 3 is not on the surface. 2 times 3 plus 1 is 7. The third prime. Because that's all we're doing here. We're saying if n does not equal this, then 2n plus 1 is not going to be an odd composite. And 2n plus 1 has to be an odd number because that only generates odd numbers. So any number that's not on here, when you plug 2n plus 1 in, you will get a prime. And if you order the numbers that are not in this on this surface, you get all the primes in order. So 4 is on this surface. So if we were to do 2n times 1 on that, that's 9. Well, hey, obviously 9's not prime. 3 times 3 or whatever. But now the next number that doesn't appear is 5. And 2 times 5 plus 1 is 11. 11 is prime. The next number that doesn't appear is 6. Because that corresponds to 13, which is prime. Well, 7 appears, so that won't work. The next number that doesn't show up is, I'm only going to do a few more. You can check all these for yourself, but you get the idea. I want to drive it home. So the next number that doesn't appear is 8. And 2n plus 1 on that is 17. The next number is 9, which corresponds to 19. Well, 10 is here. The next one is 11, which corresponds to 23. And you can just keep going on and check these all you want. 12 is here and 13 is here. The next one that doesn't show up is 14, which is 29. 2 times 14 is 28, plus 1 is 29. So I just want to establish here that by using this technique, where you're looking for odd numbers that are not odd composites, you can generate this surface that tells you that 2n plus 1 is a prime number. So any number not on here times 2n plus 1 gives you a prime number and in order. Great. Excuse me. So now, likewise, the second surface is all the n such that 2n plus 3 will be an odd composite. So that choosing one where n's not on this surface tells you that the 2n plus 3 is a prime. Okay. So choosing a number of n that is not on either surface makes them both prime, and it generates a twin pair. And we'll do some examples of that. So in fact, like surface 1 does alone for the primes, choosing a number not on either generates all twin pairs without exception, and when ordered, generates them in order. Since choosing a natural value n that is on neither surface will always generate a unique twin pair. So that if we could show that there are infinite numbers that are not on both of these surfaces, then you'll have infinite twin primes. So that's the whole premise of this proof right there, and what we're going to have to prove and show. So if a number is not on this first surface, it generates a prime. If a number is not on this second surface, it also generates a prime, which happens to be 2 away from this first one. So if we find numbers that are not on either surface, it generates a twin pair. So let's go through and try again like we did for the primes, just so you can see it in action. So the first number that's not on this surface is 1, and 1 is not on this surface too. You'll see it's the first one that appears is 3. So 1 and 2 are not on either of these surfaces. And when I plug in 1, I get the first prime 3, but that's for the first pair, which is 3 and 5 are the first pair of twin primes. Similarly, 2 is not on either of these charts. And so 2 is for 5, which is for 5 and 7, the second pair of twin primes. Great. So now what's the next number that does not appear on either of these surfaces? Well, 3 does, 4 does, but 5 does not appear on either of these surfaces. And 5 times 2 plus 1 is 11, corresponding to 11 and 13. The third pair of twin primes. So let's keep going, 1 or 2 more. So 6 is here, we can't use that. 7 is here, we can't use that. Oh, but look, there's no 8. There's no 8 on either of these. And 8 times 2 is 16, plus 1 is 17, corresponding to 17 and 19, the next pair of twin primes. See where this is going? So 9 is here, that won't work. 10, 11, 12, 13. Now, I don't think do we have C of 14? No. We don't have any 14 on either surface. And 14 times 2 is 28, plus 1 is 29, corresponding to 29 and 31, the next pair of twin primes. So anytime you find a number that is not on, it can't be on either surface, meaning it's not on both. It's not on either of these. 2n plus 1 times that number will give you the first pair of twin primes. This is the real root of this proof, or the heart of what we're going to have to prove, so I'm driving it home and showing you the logic and why it works. So that's it. That's it right there. There's your goal. If you can prove that there are infinite numbers which do not appear in either of these surfaces, obviously not just this little value of chart, but out to infinity, the entire chart, you have to show that there's infinite numbers that don't appear on either of these. But if you could do that, you've just shown that you have infinite twin generating numbers then. So that's what we're going to do. We're going to prove that there's an infinite amount of numbers that don't appear on either of these surfaces, and therefore there's an infinite number of twin primes. Seems pretty easy and straightforward in that sense. Now, it's actually hard to do. The very first time I tried to figure out how to prove that there was a way of an infinite number of, I like to call them holes. If you think about them as holes in these charts, holes are the numbers that don't show up, right? So if there's an infinite number of holes between the two charts that show up on neither, then you have infinite twins. And the first way that my mind eventually proved it was much more convoluted than over time I found a better way. So we're going to talk about the better way first because it just makes it more concrete. And I do have to say that a later part of this proof becomes it's actually, in one sense, it's kind of easy. It's, again, college level and there's not too much to this that's really that hard. But there is a part of it that's very tedious and analytic. So depending on how well you handle certain tedious or analytic algebra tasks, and it gets hard to say in words a bit conversationally, but it's actually fairly straightforward. So we'll stumble through it and get through it. But if anyone else looking wants to see that and can do it more easily on their own, I personally think that there are much more easy ways to prove that there are infinite numbers which do not appear on these two surfaces than the way I found. But hey, one way is still as good as the next. It's just maybe somebody will find a better, quicker way, and I think there is. But this is the ways that my mind was able to find a proof, to find and show, hey, there's an infinite number of values that don't appear on either of these charts, either of these two surfaces. That's all you have to do. If you can do it, if you can come up with a way on your own, you've just proven the twin prime conjecture. And if for those who are still not convinced, sit down and go back through what I just said here with why this works. Because I really haven't had to prove or do anything yet. I'm just setting up the givens and the premise here. But you can go through these charts out to infinity to your heart's content, and anytime you find a number that's not on both, you'll generate a twin pair by doing 2n plus 1. Okay, great. I think you get that at this point. Let's move on a bit. Now, how are we going to prove this? Okay. And I say at this point, it may intuitively seem that there are an infinite number of twin primes. Since if you have a sense of surfaces and numbers, these surfaces are kind of sparse looking, and there's tons of values which don't appear. You'd kind of think like, yeah, this looks like we're going to have no problem. Again, it gets a little trickier than you might think. But your first intuitive guess at this point should be, yeah, there's infinite numbers not on this one. There's infinite numbers not on this one. They probably cross, and there's probably plenty of infinite numbers that generate infinite twins, which is what we should expect because most people think that the infinite twin prime would be true. Okay, great. So it may intuitively seem that there's an infinite number of twins since one can always find another value not on either surface. And this makes sense. As a quick initial verification, try the first few values. Excuse me, I'm hiccuping. That's what I explained to you. I walked you through some examples. So that's all this next part is saying, hey, look for some examples. And then I just reiterate kind of what I just reiterated to you for the last 5 minutes or 10 minutes. To reiterate, in order to prove the twin primes, it must be shown that there are an infinite number of natural numbers not in the range of either of those surfaces when their domains themselves, the A, B, C, and D, are the natural numbers. In concept, it's very straightforward, but for me, this is easier said than done. Yeah, at that point, I feel like some math guys would have an easier time. Guys very familiar with modular arithmetic will have an easier time with this than I did, but I still found a way. Over time, I found few similar ways to do it, some better than others, more easy to explain than others. And here I describe the easier of the methods that I had out of my two. So this next section I call the values within or outside the range of the surfaces. So the general method that we're going to use to show that there are infinite numbers outside of the range of both of those surfaces is as follows. So we're going to take each, and I'll read this a bit, and then of course I'll go back and scroll back or show you examples or whatever, but I just want to kind of get on to the next part and start doing it. We're going to treat one variable as a constant in order to decompose the surfaces into an infinite number of lines, and thus assign each line to a row as shown in the tables. We're then going to show that there are infinite numbers outside the range of each specific row or line. And next, we're going to show that there are infinite numbers outside the range of any two adjacent rows. And I'll go back up and recap this in a second. And then we're going to show that there are infinite numbers outside the range of any number of consecutive rows, and thus not on the surfaces. So let me go back to these two charts, which I said this is why it makes it handy visually, just to kind of get you familiar with what you have to try to do and how I saw it. You might find a better way, and that's great. Please share it with me if you do, and share it with other people too. So we're looking for numbers that are not in this surface and not on this surface, and we have to show that there's an infinite number of those. So first, we're going to show that there's an infinite number of numbers that don't appear on this very first row. And this first row, we're going to turn into a line. We're going to use point slope formula and turn this first row into a line. And we're going to show that there's an infinite number of values that don't appear on this row. And same for this surface. Infinite number of values that don't appear on this row. And we're going to show there's an infinite number of values that don't appear on this first row and this first row at the same time. Then we're going to show that there's an infinite number of values, that there are an infinite number of values that don't appear on this first row and this second row. Same down here, this first row and this second row. And that there's values that don't appear on all four of those rows. And then lastly, we're going to show that you can do it for any consecutive number of rows that you want. That there are numbers that don't appear on any consecutive rows on both charts. And that's going to be the general strategy that we take. And if we can write down some formula for the numbers that don't appear, or at least you don't even have to write down the formula for all the numbers that don't appear in either chart. You can take an infinite subset of that infinite set. So as long as you can come up with some formula that you can show always generates numbers that are not on either chart and are in no rows, you're golden. And that's what we're going to do. So in the end here, I don't actually have a formula that generates all of them, just an infinite subset of them. But an infinite subset of an infinite set is still an infinite set. So that's fine. And that's going to be our general strategy. Show that there are an infinite not in each row, each consecutive row, any number of rows, and any number of rows between the two charts. Great. So here I just reiterate that the surfaces are symmetrical, from this point of view, AB plus A plus B, and that's why they're diagonalized down that diagonal. So so all the numbers in this lower half of the diagonal repeat from the upper half. So we can use either part that we want. We don't have to check the whole chart because it's just the chart duplicated by itself, folded over the diagonal. So we really only have to check either the upper triangle or the lower triangle, including the diagonal, of course. And same for this chart. And that's all I'm saying there. Let's see. Okay. So here, let me read and then I'll paraphrase. Look at the values in rows 1 where A and C are held constant and set equal to 1. That is, and I do the math here, the surfaces simplify into these lines. So like I said, now we're going to go line by line and then adjacent lines and then all lines. And this becomes very tedious, but that's what we've got to do. So what am I saying here? I'm saying that so let's say this, we're just going to look at this first row. So we're going to set one of these values to 1 for the first row. So that if A is 1, for example, then that condenses down into 2 times B plus B, which is 3B plus 1. And indeed, you can see that the line, the y equals mx plus b, or the point slope formula for the line here on this first row, now we're just looking at the values in the first row, is indeed 3, you could think of it as 3x plus 1, right? 4, 7, they differ by a value of 3. That's just when one of these variables is 1, you get the row 4x or 3x plus 1. And since this chart is just the same as this surface, but slid down 1, then these rows have the same slope, and just the y-intercept is slid down by 1. So while this one here is 3x plus 1, this one ends up just being 3x. 3, 6, 9, 12, 15, 18. And that's just by plugging a 1 in for C or D, and then condensing. So that's all we're saying next is we notice that we can write each row as a line. And that the first row for this one is 3x plus 1. And that the first row for this one is 3x. Okay. Or 3x plus 0, if you want to think about it that way. So that's why you're seeing here. 3x and 3x plus 0 are the two lines that represent those first two rows. And this can be done for any row. And you could see what the equation for the line is for that row. So if you'll notice, the next row is 5x plus 2 and 5x plus 1. The next row, row 3, is 7x plus 3 and 7x plus 2. And row 4 is 9x plus 4 and 9x plus 3. So we can just verify that. For those who can start to see the pattern, a pattern emerges very quickly because these aren't really complicated surfaces. So this one's 3x plus 1 and 3x, or 3x plus 0. This one's 5x plus 2, and so this is 5x plus 1. This one is 7x plus 3 and 7x plus 2. And if you haven't noticed the pattern already for what the equations of these lines are going to be, well, the slope is going to be the odd numbers, 3x, 5x, 7x, 9x, 11x. And the y-intercepts are going to go up. So this is 3x plus 1 and 3x, 5x plus 2 and 5x plus 1, 7x plus 3, 7x plus 2. So while the slope, the important thing to notice is that the slopes are going to be all the odd numbers, and the y-intercepts are going to be like 1 and 0, 2 and 1, 3 and 2, 4 and 3, 5 and 4. It's just going to be increasing numbers that are 1 apart. So that's the pattern that you see for the equations for all the rows. And I guess I could just do an example, like on the third row, just to really drive it home. The third row is, so it's going to be 3, 5, 7. So that's 7x, and it's plus 3 and plus 2. So you'll see 7x plus 3 is 10, 17, 24, where x is 3, it'll be 21 plus 3, 28 plus 3, 35 plus 3. This is just the 7 tables plus 3. And here on the third row, it's the 7 tables plus 2. So that's all we're driving home here, is that the rows on both of those charts can be written as lines. And here, for example, I show you the first 4 rows, the equations of the lines for the first 4 rows. Okay, great. Then I just repeat what I said here. Notice the slopes of the odd numbers. And now we're going to ask ourselves, so those lines that we just made are the values that do appear in the range of the surfaces. Those are the values that the surface generates, or both surfaces generate. But now we want to look at the values that are not generated in the rows on those surfaces. That is outside of the range. The ones that are going to possibly give us our infinite twins. Okay. So, and eventually I won't keep scrolling back to this, but for now it's just easier while I'm talking about it. Eventually we'll move on to stuff where I won't need to scroll back to these charts. Now, if a number doesn't appear in the first row, it might be somewhere else in the chart. We have to show that it appears nowhere. But just considering these first 2 rows now, we're only looking for numbers that don't appear in either of the first 2 rows. Because obviously if they appear in the first 2 rows, then they're on the chart. We can't use it. So if it has a chance of not being on the chart anywhere, it certainly can't be in the first rows. Can't be in any rows, but it can't be in the first row then. So if we said that this line is 3x plus 1, and this one is 3x plus 0, well, if you know anything about modular arithmetic, or the idea that there's only one more choice here for numbers that don't appear in the first row, are the 3x plus 2 values, right? So these are the 3x values and the 3x plus 1 values. 3x plus 2 values don't appear. But if we get around to 3x plus 3 again on the y-intercept, that's the same as 3x plus 0, just shifted by 1x. So we notice that the values that don't appear on the first rows of either surface, not the first prime surface or the second prime surface, the values that don't appear in the first row are the 3x plus 2 values. Those values do not appear as numbers in the first row. They might be somewhere else, but we're not worried about that right now. We have shown that they don't appear anywhere in the first rows, because the first row values are either 3x or 3x plus 1. Okay, great. So we're looking for values that are not in the first row. So this is not 3x plus 2. Now for that second row, we said it was 5x plus 2 and 5x plus 1. So the values that don't appear on the second row have to be of the form 5x plus 3, 5x plus 4, or 5x plus 5, which is the same as 5x plus 0. So now this is just doing some modular arithmetic here, that we notice a pattern to the values that are not going to appear in each row. So the first row, so since we're only using 2 equations for each row, but we're going up by odd numbers on each row, there are more and more lines for each row of values that don't appear. And I guess at this point I can go down back to here and show that. So the first rows between both of them, the values that do not appear must take the form 3x plus 2. For the second rows, the values that are not going to be in either row either have to be of the form 5x plus 3, 5x plus 4, or 5x plus 5. And you can start to see the pattern here. Most people, or people familiar with this, would start to be able to see the pattern if you sit with it for a little bit. So all values not on the third row, well, the third row is 7s. And there's always going to be 2 values that aren't there, but all the rest of the modular remainders are not going to be values on those, just on those rows. They might appear somewhere else, but they won't be in that row. And maybe some of you can see where we're going with this. So for the 7 row, the values are 2 and 3 that are there. But the ones that aren't going to be there are 7x plus 4, plus 5, plus 6, plus 7, and plus 8. Of course, 7 is the same as plus 0, and 8 is the same as plus 1, if you're in modular and you wrap it back around. And you can say that for any row. So for the first row, there's one line that represents all the values that are not there, or for the first set of rows, I should say, because we're doing it between both surfaces. For the second rows, there's 3 lines that represent the values that are not on those rows. For the third row, there's 5 lines, and so forth and so on. For the fourth row, there's going to be 7 lines. For the fifth row, there's going to be 9 lines. But those lines are going to represent the values that are not going to appear in either of those rows. Great. So I just say notice that the slopes are the odd numbers, that the y-intercepts span a consecutive range, and that they increase by 1 for the elements down the rows. So that's all I'm saying here is what I just explained to you. So in order for a number to not be on either of those surfaces, it must not appear on any row on either table for the surfaces. 9, 10, and 11, these 3 sets here, for example, show the general pattern for all values not in any specific row, which is what I just said. The next step is to use that pattern to find values which are not in any and all rows. And I repeat, also due to the modular nature of the lines, that the y-intercepts greater than or equal to the slope create congruent sets of values with another line and set of values that could be associated with that row, which is just the modular part. 7x plus 8 is the same as 7x plus 1, except for the first value, of course. So if you can see where we're going to go here, now that we've split these surfaces into rows and we've shown which values are not on each row, if a number is not going to be on either of those surfaces, they somehow have to come from this set of lines. Meaning we know that the numbers that are not going to appear on that surface have to be of the form 3x plus 2. That makes them not in the first row. But they also have to be numbers of the form either 5x plus 3, 5x plus 4, or 5x plus 5, which is just 5x. They also have to be numbers that are of one of these forms, and so forth and so on. So if you could show that with this pattern, there's an infinite number of numbers that are not of this form, one of these forms, one of these forms, one of the next forms, and so on ad infinitum, then you've proven there's an infinite number of twin primes. Let's see what my time is, because I knew this was going to take a while, but I want to keep these to like an hour, and then just for uploading or whatnot, and then I'll stop it here in 5 or 10 minutes, and I'll just start a second one or whatever, however many I need, that's fine. I just don't want to do it in all one video rather than have to split it up later using a splitter or something. So to find at least one set of values not in any row on either surface, and thus not on either surface, begin by noticing for rows 1 that all the values greater than the first elements of those rows, which are all of the form 3x plus 2. So again, I'm saying stuff before I even read ahead in the paper, so I'm just repeating here a little bit. That is this infinite set of 3x plus 2, which I just start giving you those values, 5, 8, 11, 14, 17, 20, and so on. They're not on either row 1. So those are the values that you'll never see on row 1 of either one of those charts, you know. So now put that aside for a moment, and we're going to do the same thing for the second row. We said that the 5x plus 1 and 5x plus 2 are excluded because those are the values that are on those 2 rows. However, that equation 10 was the other 3 sets of values, 3 lines that are never on that row, on either one. The first set is 5x plus 3. So what I say here is we have to work with 3x plus 2 because that's the only choice we have for that first row. But for the second rows, we could choose any of these because none of those values will appear on either surface. So this proof uses all the first values that don't appear in each set of rows or lines that we have to choose from. So we're going to be focusing on the 3x plus 2, the 5x plus 3, 7x plus 4. The next one would be 9x plus 5, 11x plus 6, 13x plus 7, and so forth and so on. We're just increasing the odd numbers, and on the back we're increasing by 1. 3x plus 2, 5x plus 3, 7x plus 4, 9x plus 5, 11, 6, 13, 7, 15, 8, and so forth and so on. So that's all I'm saying here. But what does that mean? I'm reiterating it. So that means numbers that are the intersection of the sets 3x plus 2 and 5x plus 3 are not in either of the first 2 rows, right? If we have a number that's of the form 3x plus 2 and 5x plus 3, that won't be on either of those first 2 rows. And then if we take any of those numbers that are also not in 7x plus 4, then those numbers are not going to be on the first 3 rows. If we were to take the next one, 9x plus 5, then those numbers won't be on the first 4 rows. And so forth and so on. And this is how we're going to show that there's an infinite number that aren't there. And some of you might see it already and say, yeah, that's it. You got it. That makes it pretty easy. But we want to prove it a little bit more rigorously and show that there's an infinite set from this pattern that we're building here that don't show up. So continuing the process means that finding an infinite number of values in the intersection of the sets of all those lines so that there's an infinite number of values not on any row and therefore not on either surface. So now we've turned finding the twin primes, prove that there's an infinite number of twin primes, into proving that there's an infinite number of elements in the intersection of all these sets, if you think of the lines as the sets. And if you can prove that there's an infinite number of values, and again, I think somebody with modular math will be like, oh yeah, it's just that. And they'll be able to quickly say it and do it and be like, oh, you didn't prove it this way? Like, I think there's going to be some people who once they learn this technique, are going to find a much easier way than what I'm about to show you, which is going to take another hour or two of very convoluted arithmetic to prove that there's an infinite number of elements in that set. But that's what we're going to do. And please show me the faster way when you guys see it. And you're like, oh God, duh, dude, you didn't see it this way? I'm like, nope, sorry, this is how my brain got it first. So maybe I want to stop here because this is right before an hour. And maybe this is a good place to stop. But you have a sense of what's going on now. You've learned about the surfaces. You've learned why those values generate primes in twin pairs. And if we can show that there's not an infinite number of values on either of those surfaces, you've shown there's an infinite number of twins, since each one will generate a twin pair for you. The next step is going to be the infinite values not in the range. And I start to generalize it a little bit more. So let me stop here, grab a little thing to drink. Some water. I might grab a little bite to eat or something. And then my throat gets a little dry and scratchy, but I'm kind of in the mood to make more of these. So I'm thinking I'm going to at least do the next part tonight, and I'm going to crank out another one of these videos. But for now, I'm going to take a break and leave it here. This will be part 1, and you can look for part 2 once I get that recorded. So I hope you're enjoying this, what's going to be the proof of the twin primes, or my way of thinking that I proved it, or go about showing that I proved it. And here you've got the general basis for it. Feel free to ask some questions, and thanks for watching. We'll see you here soon for part 2.